Imagine you are standing outside on a warm July night. The Milky Way is stretched above you like a brushstroke of ancient light. You look up. You feel small. You feel, for just a moment, like the universe is watching you back. Now imagine that feeling is not a metaphor. On July 1st, 2025, a telescope in the high desert of northern Chile pointed its automated eye at a patch of sky near the center of our galaxy. It was a routine night. It always starts as a routine night. The system, a network of robotic cameras called ATLAS, the Asteroid Terrestrial Impact Last Alert System, was doing exactly what it was built to do, scanning the dark, looking for rocks that might one day end civilization as we know it. Boring work, patient work, the kind of work that, paradoxically, requires no human presence to perform and yet exists entirely to protect human presence from being extinguished. The cameras swept. The computers processed. The algorithms sorted signal from noise the way a gold miner sieves gravel from a river. And somewhere in the data stream, between one frame and the next, a tiny smear of photons landed on the detector that should not have been there. A faint smudge of light, magnitude 20, so dim that if you held up a flashlight in the middle of Times Square, its light would be millions of times brighter than what this camera was recording from a distance of hundreds of millions of miles. The human eye, unaided, would not have perceived it even if you were looking directly at it in a perfectly dark sky with perfect vision. But the camera caught it. And when the data was processed and the orbital mechanics were calculated, when the computers began asking the most fundamental question in all of astronomy, the question that underlies every sky survey ever conducted, where does this thing come from? The answer came back wrong. Not wrong like a miscalculation, not wrong like a software bug, wrong like a revelation, wrong in the way that changes everything. This object was not from here. It had not formed in our solar system. It had not been drifting in the cold storage of the Oort cloud for 4 billion years, waiting for a gravitational nudge from a passing star to send it sunward on a long elliptical journey. Its trajectory, the elegant, closed parabolic signature of every comet and every asteroid that has ever belonged to our solar neighborhood, was not a parabola at all. It was something wilder, something mathematically unmistakable, something that said, in the language of orbital mechanics, I am passing through. I do not belong here. I am not stopping. The object had a hyperbolic trajectory, an eccentricity of approximately 6.1. Let me give you a number to feel in your chest. A comet that belongs to our solar system, a comet that formed here and will always be gravitationally bound to our sun, has an eccentricity of somewhere between 0 and 1. An eccentricity of exactly 1 describes a parabola, the theoretical boundary between bound and unbound. An eccentricity greater than 1 means the object is moving too fast for our sun's gravity to hold it. An eccentricity of 6 means this thing was moving with such speed, such velocity, such excessive kinetic energy relative to our star, that gravity could not grab it no matter how hard it tried. It came from somewhere else in the Milky Way. It is going somewhere else in the Milky Way. And for a brief, extraordinary, geologically instantaneous window of time, a handful of months, it passed through our neighborhood. Scientists gave it a name, 3I/Atlas. The 3, because it is the third interstellar object ever confirmed to have visited our solar system. The I because interstellar. The Atlas because that is the telescope that first captured it on its sensor. Simple, precise, bureaucratic in the way only scientists can be bureaucratic when they are staring at something that might rewrite everything. 3 interstellar objects in the entire recorded history of human astronomy. Think about that number. We have been watching the skies seriously with purpose-built instruments for roughly 400 years. In all of that time, across the thousands of years of naked eye observation before that, across the full span of recorded human curiosity about what lives in the dark above us, we have confirmed exactly 3 visitors from beyond our solar system. The first was Oumuamua in 2017. The second was Borisov in 2019. And now, 3I/Atlas in 2025. 3 in 8 years. After 400 years of seeing 0. Each one stranger than the last. Each one teaching us something we did not know we did not know. Let us pause here, because the number 3 deserves more attention than it typically gets in news coverage. 3 interstellar objects in 8 years, after 400 years of seeing 0. That is not a statistical fluctuation. That is a signal, and the signal is this: we were not looking carefully enough before. Now that we are looking, we are finding that the space between stars is not as empty as we imagined. For the first 3 centuries of modern astronomy, from Galileo's first telescopic observations in 1609 through to the discovery of Oumuamua in 2017, the assumption embedded in almost every model of our solar system was that it was essentially self-contained. Comets came from the Oort cloud, our cloud, the vast spherical shell of icy debris surrounding the Sun at distances from 1,000 to 100,000 astronomical units. Asteroids formed in our asteroid belt, between Mars and Jupiter, leftover material from the planetary formation process that never assembled itself into a planet. The occasional unusual orbit, the rare object that arrived from an unexpected direction with too much velocity, was explained as a perturbation within our own system, a comet scattered inward by a gravitational interaction with Neptune, an Oort cloud object perturbed by a passing star. Nobody seriously expected to regularly observe objects from other star systems. Not because the physics forbade it. Astronomers Fred Adams and Gregory Laughlin, working in the early 2000s, calculated that every star system should eject enormous quantities of debris during the chaotic early phase of planetary formation. Comets flung outward by the gravitational pinball of forming giant planets, asteroids scattered by close encounters between growing planetary embryos. Some fraction of that debris would reach escape velocity and enter interstellar space. Some even smaller fraction would, through the accumulated gravitational redirections of billions of years of galactic travel, eventually pass through another star system. The theory was solid. The problem was detection. The objects would be small, fast, and extremely faint, and the sky surveys of the 20th century simply did not have the sensitivity, the cadence, or the automated analysis systems to catch them. What changed was not the universe. What changed was us. Atlas, the Pan-STARRS survey, the Zwicky Transient Facility, these modern robotic sky survey systems represent a generational leap in humanity's ability to systematically monitor the entire visible sky, repeatedly on timescales of days, with sensitivity sufficient to detect magnitude 20 objects before they recede beyond reach. We did not discover more interstellar objects because more of them started arriving. We discovered them because we finally built the eyes to see what was always there, passing silently through our neighborhood, undetected in the dark. This distinction matters profoundly. If 3 interstellar objects have been detected in the 8 years since our surveys became capable of catching them, then the actual rate of passage through the inner solar system is far higher, because our current surveys catch only the brightest, largest, slowest-moving fraction of interstellar traffic. Statistical analyses published in the wake of 3I/Atlas suggest that a new interstellar object of detectable scale may pass through the inner solar system as often as every 5 years. And those are just the ones big enough and active enough for current instruments to register. The smaller ones, the darker ones, the ones moving too fast for our cameras to accumulate more than a blur, pass through uncounted and unnamed. The solar system is not a quiet, self-contained neighborhood. It is a busy cosmic intersection, and we have only just installed a traffic camera. There is something else worth noting about the 3 objects we have detected, and it is something that Avi Loeb has written about in detail, drawing on kinematic analysis that traces each object's trajectory backwards through galactic history to infer its origin. Oumuamua, the first interstellar visitor detected in 2017, appears to have come from the thin disk of the Milky Way, the flat, dense, younger population of stars where our own sun resides. It was relatively young by interstellar standards, perhaps 1 billion years old. It moved at about 26 kilometers per second relative to the sun, arriving from a direction roughly consistent with the local stellar neighborhood. 2I/Borisov, detected in 2019, was a more conventional interstellar comet in many respects. It had a visible coma and tail from the moment of discovery, and its composition, while unusual in some ways, was recognizably cometary. It was approximately 1.7 billion years old, also from the thin disk population, and arrived at about 32 kilometers per second. Then came 3I/Atlas. Faster than both predecessors, roughly 58 kilometers per second at infinity, the velocity it had when our sun's gravity began to pull at it. Kinematics pointed not to the thin disk but to the thick disk, the older, higher-altitude population of stars that orbits the galactic center on tilted, slower precessing paths. Thick disk stars are metal-poor, Formed in an earlier era of the galaxy's history when the Milky Way's chemistry was different, its stellar population younger and hotter and shorter-lived. The Hopkins et al. Analysis estimated 3I/Atlas's age at 7.6 to 14 billion years with 68% confidence. Not just older than our solar system, potentially as old as the universe itself. It came from a star that formed in the galaxy's first few billion years, a star that has long since ended its life, gone through whatever death sequence its mass decreed, and scattered its remaining material back into the interstellar medium. 3I/Atlas is, in a very literal sense, an orphan of a dead star, an object that outlived its creator and has been traveling alone, through the dark between stars, for longer than our sun has existed. There is a certain melancholy to this, if you let yourself feel it. The object was old before the Earth formed. Whatever star it came from collapsed and ended before the first animal ever crawled out of an ocean anywhere in the history of life. And now, after billions of years of solitary travel, it passed within 170 million miles of the planet where a civilization had, just barely, developed the instruments to notice it. We looked past. Let us talk about the universe as it actually is, because the universe does not care about your comfort zone. The universe operates at scales the human brain did not evolve to comprehend intuitively, and so we must use numbers and analogies to build a mental scaffold that can hold the weight of what we are talking about. Our solar system, from the Sun to the outermost edge of the Oort cloud, spans approximately 2 light-years in diameter. The nearest star to our Sun, Proxima Centauri, sits 4.2 light-years away. The Milky Way galaxy is roughly 100,000 light-years across. There are approximately 200 billion stars in our galaxy, and our galaxy is one of an estimated 2 trillion galaxies in the observable universe. When you fire an object from one of those 200 billion stars at a velocity sufficient to escape its home system, when that object is ejected into the interstellar void by the gravitational chaos of a young planetary system, or by a close stellar encounter, or by any of a dozen other mechanisms that populate the space between stars with orphan debris, the chances of that object accidentally, randomly, blindly wandering into the tiny gravitational funnel of our particular sun, threading between our particular planets, approaching within optical detection range of our particular planet, at the particular moment in history when our particular civilization happens to have built the particular automated telescope that would catch it at magnitude 20 on a July night. Those odds are, conservatively speaking, impossible without some hidden architecture to the universe that makes them less impossible. And yet it happened 3 times in 8 years. The mainstream scientific community, NASA, the European Space Agency, the International Astronomical Union, looked at 3I/Atlas and arrived at a measured, careful, defensible conclusion. This is a comet. An ancient one. A very old comet from another star system, probably ejected from its parent stellar system billions of years ago, wandering through interstellar space since before our sun existed, until some combination of galactic dynamics and statistical chance delivered it to our doorstep at this particular moment in cosmic history. Natural, explicable, extraordinary but not mysterious in a way that required exotic explanations. And then Michio Kaku opened his mouth, and the world leaned in. Michio Kaku is not a man who speaks quietly about small things. He is a theoretical physicist, a professor at the City College of New York, and the author of books like Hyperspace, Physics of the Future of Humanity, and Quantum Supremacy, books that sit on the shelves of people who want to understand the cosmos without spending a decade earning a doctorate. He is, in the best possible sense, a translator. He takes the dense, heavily mathematized machinery of modern physics and renders it into language that a thoughtful teenager can follow, that a curious grandmother can engage with, that a skeptical engineer can respect. He appears on television not to dumb things down but to light things up. He has spent his career making the frontier of human knowledge feel personally relevant. When 3I/Atlas was discovered, Kaku did not immediately declare it alien. He is too careful for that, too experienced. He had watched Oumuamua arrive in 2017 and generate a frenzy of speculation that embarrassed some of his colleagues and delighted science communicators, and left the public confused about where the evidence actually stood. He knew the terrain. He knew that the gravitational pull of an exciting hypothesis can be almost as powerful as the actual gravity that governs orbits. But he also knew something specific, something precise. He knew that there is a particular measurement, a particular number, observable with existing instruments, that separates a rock obediently following Newton's laws from something that might be choosing its path. He called it the energy boost. In October 2025, with 3I/Atlas hurtling toward perihelion, its closest approach to our sun, scheduled for October 29th, Kaku appeared on television and laid out a specific, falsifiable prediction. He said, "Watch for what happens when this object passes the sun. When it swings around our star in the gravitational slingshot that all interstellar visitors execute on their way through, watch to see whether it gains additional speed. Not the speed it gains from the sun's gravity that is expected, that is calculated, that we can predict to 7 decimal places. Watch for speed beyond that. Watch for an extra boost. A boost that the equations of celestial mechanics and thermal rocket effects from ice sublimation do not account for." He said these words on camera, in public, with full awareness of what he was doing. Watch for it. On October 30th, starting then, we're going to track it to see whether it gets an extra boost of energy. If so, it means we are being visited. Not it could suggest. Not it might warrant further study. It means we are being visited. That is the warning. That is the moment, a physicist of global reputation in plain English on national television, that started the most consequential scientific argument of 2025. And then October 30th came. Before we reach October 30th and what the instruments recorded in its aftermath, we have to go back. We have to talk about what was already wrong with 3I/Atlas before Kaku ever issued his warning. Because the energy boost was not the first anomaly. By the time he went on television, a list of data points had already accumulated that did not sit neatly within standard models of comet behavior. Not 1 or 2 puzzles. A collection, a growing ledger of strange. Let us go through them one by one in the patient way that science actually works, not with drama but with data. The first anomaly is the tail, or rather, the character of it. When a comet enters the inner solar system and approaches a star, heat vaporizes its surface ices. Water ice, dry ice, carbon monoxide. These sublime and carry dust off the nucleus, creating the glowing cloud called a coma and the streaming tail that makes comets visible and beautiful. The tail always points away from the sun. Always. This is not a coincidence. It is physics. Solar radiation pressure and the solar wind both push material away from the star, and so cometary debris streams downwind, in the anti-solar direction, like smoke trailing from a vehicle moving through air. Every comet humanity has ever catalogued, across centuries of observation. Halley's, Hale-Bopp, McNaught, Lovejoy, the countless anonymous visitors that grace our skies and fade before most people notice them. Everyone follows this pattern. 3I/Atlas had a coma. That much was confirmed in early images from July 2025, visible at the Canada-France-Hawaii telescope and the Very Large Telescope. But it also had something unusual, a persistent anti-tail, a jet of material pointing toward the sun. Astronomers call this a sunward jet, and while they are occasionally observed in solar system comets under specific geometric circumstances, when the viewing angle from Earth makes it look like material is pointing at the sun even though it is actually pointing away, those cases are brief, angle-dependent illusions. They disappear when the viewing geometry changes. The anti-tail of 3I/Atlas persisted from July through August and remained clearly visible through November 2025. It was not a geometric illusion. It did not go away as the object's position relative to Earth changed. Harvard's Avi Loeb noted that the high-rise imaging taken at 3I/Atlas's closest approach to Mars confirmed a glowing extension ahead of the object along its direction of motion. Ahead, in the direction of travel. Not behind it, streaming in the solar wind. In front, like something was being expelled or emitted in the direction the object was heading. The second anomaly is the color. This one requires a small amount of physics to appreciate fully, so stay with me. Comets are red. Not dramatically red, you cannot see it with the naked eye, but spectrally measurably redder than the sun. There are 2 physical reasons for this. First, dust particles in a cometary coma scatter sunlight in ways that preferentially reflect longer wavelengths, shifting the reflected light toward the red end of the spectrum. Second, the surface of a comet nucleus, being far colder than the sun's photosphere, naturally emits and reflects in a redder profile. These effects combine to make comets reliably red, predictably red. The redness of a comet is one of those observational facts that has been so consistently confirmed across so many objects that it has become a baseline expectation. 3I/Atlas was red when it arrived. Its initial spectral slope, measured in July 2025, was 17.1% per 100 nanometers, solidly red, comparable to other interstellar objects and to primitive solar system small bodies. Then it approached the Sun, and as it passed perihelion in late October 2025, something changed. The object became bluer than the Sun itself. This is not supposed to happen. Under every standard physical model for comet behavior, heating by the Sun should not produce a blue-ward color shift that takes the object to a spectrum bluer than the star heating it. If anything, heating should drive more red, more dust emission, more sublimation of reddening organics. The unexpected blue signature near perihelion was noted in multiple independent spectral datasets from ground-based observatories and space-based instruments. It was real, and the explanations offered for it were strained: exotic chemistry, unusual composition, some interaction between the object's nucleus and the solar radiation field that had not previously been observed. Or, as Loeb suggested in a Medium post that received more scientific attention than many formal papers. Alternatively, the blue coloration might be the spectral signature of something happening internally, something that was not solar heating. The third anomaly is the nickel. In 2021, a study published in the journal Nature confirmed something genuinely surprising. Many solar system comets emit nickel atoms in their comas. This was a significant discovery. Nickel is a metal. It has a high boiling point. At the cold temperatures where cometary comas exist, far colder than any laboratory on Earth, deep in the darkness of space, you would not naively expect metallic nickel to be vaporizing off a dirty snowball. The explanation the scientific community settled on was organic. Complex nickel-bearing organic molecules decomposing as they are heated by the Sun, releasing nickel atoms as a byproduct. Reasonable. Satisfying in the way that good science is satisfying. A strange fact carefully explained. 3I/Atlas emitted nickel too. But the nickel signature in 3I/Atlas's coma, particularly in the months before perihelion, was anomalously abundant. Much stronger than what models calibrated on solar system comets would predict for an object of its measured size and estimated mass. Loeb cataloged this as one of his key anomalies. The quantities were inconsistent with simple organic breakdown. If you were inclined toward more exotic interpretations, and Loeb is professionally inclined toward exactly that, which is both his strength and the source of his critics' frustration, you might note that anomalously high nickel abundance is consistent with the presence of processed metallic material. Engineered metallic material. The kind of material that might constitute the structural components of a manufactured object that has been in space for billions of years, slowly shedding surface layers as it ages. The fourth anomaly is the composition more broadly. The James Webb Space Telescope, which was pointed at 3I/Atlas in an observation run that generated enormous excitement among planetary scientists, found something striking in its near-infrared spectroscopy. The ratio of carbon dioxide to water in the object's coma was 7.6, plus or minus 0.3. In solar system comets, that ratio is typically far lower. 3I/Atlas's CO2 enrichment was 4.5 standard deviations above the solar system trend. That is a number worth pausing on. In normal scientific usage, a result 4.5 sigma from expectation is extraordinarily significant. It means the deviation cannot easily be explained as a random fluctuation. Something about this object's chemistry is genuinely, measurably unlike anything in our solar system. The scientific paper that reported this finding, led by researchers from the Royal Belgian Institute for Space Aeronomy using JWST and SphereX data, concluded that the explanation was galactic cosmic ray processing. Billions of years of bombardment by high-energy particles streaming from elsewhere in the galaxy had chemically altered the surface of 3I/Atlas down to a depth of roughly 50 to 60 feet, converting carbon monoxide into carbon dioxide and building up an organic-rich radiation process crust. The researchers called this a paradigm shift, the first direct evidence that long-traveling interstellar objects are fundamentally transformed by their journey, and that when we observe their outgassing, we are sampling the processed rind rather than the pristine interior. This is the mainstream scientific explanation for 3I/Atlas's unusual chemistry, and it is a genuinely good one. But it also means that the outer shell of 3I/Atlas, the part we can actually observe, has been so thoroughly altered by billions of years of radiation that we have no idea what is underneath. The pristine interior, if it exists, is shielded from our instruments by a cosmic ray process mantle of organic crust and altered ices. We are reading the cover. The book, whatever it contains, is closed to us. Now let us talk about the age, because the age of 3I/Atlas is one of the strangest facts in this story. A study published in July 2025, led by Matthew Hopkins and collaborators, analyzed the kinematic properties of 3I/Atlas, how it was moving relative to the stars in our galactic neighborhood, and worked backwards to infer its origin. The object's high velocity relative to the Sun and the direction of that velocity, when modeled against the structure of the Milky Way, pointed to origin in the galactic thick disk. The thick disk is an older, higher-altitude population of stars orbiting the center of our galaxy at greater distances from the flat midplane where our Sun lies. Stars in the thick disk are older, poorer in heavy elements, products of an earlier era of galactic star formation. Based on the typical ages of stars in the thick disk, the Hopkins study estimated with 68% confidence that 3I/Atlas is between 7.6 and 14 billion years old. 14 billion years. The universe itself is only 13.8 billion years old. The high end of that range approaches the age of the cosmos. Even the low end, 7.6 billion years, is 3 billion years older than our Sun. This object may have been born in a stellar system that formed before our solar system's atoms were even assembled in the heart of their parent star. Let that sit for a moment. While Earth was a molten ball of rock cooling in the young solar system, 3I/Atlas may have already been 3 billion years into its interstellar journey. While the first single-celled life was struggling to survive in early Earth's toxic oceans, 3I/Atlas was halfway through what we now recognize as its billion-year transformation by galactic cosmic rays. While our ancestors were developing the opposable thumbs that would eventually build telescopes, this object had already crossed the equivalent of thousands of light-years in its slow, hyperbolic arc through the Milky Way. Cannot be traced to a parent star. The galaxy has had billions of years to shuffle its stellar populations, and the gravitational encounters 3I/Atlas experienced during its long journey have erased any clean orbital record of where it came from. We know the population it came from, the thick disk, but not the individual star. Its home star is gone, either burned out or too mixed into the galactic background to identify. 3I/Atlas is, as Avi Loeb wrote in a paper, among the elders in our cosmic block. It is a relic of a time before our Sun, before our Earth, before any life that led to us. It is older than everything we have ever touched. This is where Michio Kaku's framework becomes not just interesting but genuinely important. Kaku has spent decades thinking and writing about what it means for a civilization to be old. His books on the Kardashev scale, the framework proposed by Soviet astronomer Nikolai Kardashev in 1964 for classifying civilizations by their total energy use, explore what a truly ancient technological civilization might look like, might be capable of, might choose to do with the time and energy available to it. A Type 1 civilization, by Kardashev's framework, harnesses the full energy output of its home planet. We are roughly 0.73 on that scale today, approaching Type 1 status, expected to reach it within a few hundred years if we do not destroy ourselves first. A Type 2 civilization harnesses the full energy output of its star, a Dyson sphere civilization in the popular imagination, though the actual engineering might look very different. A Type 3 civilization harnesses the full energy output of its galaxy. Kaku has pointed out that the time gap between us and even a modest Type 2 civilization might be, in cosmic terms, small, perhaps 10,000 years more of technological development. 10,000 years. In the 14 billion-year sweep of the universe's history, 10,000 years is nothing. It is a rounding error. It is less than the age of writing. And yet, a civilization 10,000 years ahead of us in technology would have capabilities so far beyond our own that we might genuinely struggle to distinguish their artifacts from natural phenomena. This is the heart of his warning. Not that 3I/Atlas is definitely an alien artifact, but that if a civilization had billions of years, the kind of temporal head start that the thick disk origin of 3I/Atlas implies, they could have built interstellar probes that would be, by our current standards of observation, effectively indistinguishable from very old comets. Chemically altered by space, coated in cosmic ray processed organics, moving on hyperbolic trajectories, exhibiting just enough anomalous behavior, a wrong direction tail, an anomalous color shift, a nickel excess, a non-gravitational acceleration with a sideways component, to make a thoughtful scientist pause. But not enough in any single measurement to constitute proof. Kaku is not asking you to believe this. He is asking you to take it seriously as a hypothesis. He is asking you not to dismiss it reflexively, the way that institutional science has a well-documented tendency to dismiss ideas that fall outside the Overton window of acceptable academic discourse. On the night of October 29, 2025, 3I/Atlas reached perihelion. It was 1.36 astronomical units from the Sun, between the orbits of Earth and Mars, moving at approximately 153,000 miles per hour, illuminated by our star at a level intense enough to drive significant chemical activity on its surface. Every instrument that could be pointed at it was pointed at it. This was the moment Kaku had identified as the test. October 30th came. The data began to flow. In the weeks that followed, as the measurements were processed and cross-checked and argued over, a number emerged. On November 24, 2025, measurements detected a non-gravitational acceleration of 4 times 10 astronomical units per day squared. This is a very small number in absolute terms, but what matters is whether it is larger than what we would predict from natural outgassing alone. And the answer, depending on which model you used and how generously you treated the error bars, was yes, possibly significantly larger. Non-gravitational acceleration is not unusual in comets. When a comet vaporizes material, when ice sublimates and the resulting gas jets off the surface, the reaction force pushes the comet in the opposite direction, like a thruster. This is sometimes called the rocket effect. It has been measured in dozens of solar system comets, and the models that describe it are well calibrated. We know roughly how hard a comet of a given size should be pushed by outgassing, as a function of its distance from the Sun and the composition of its coma. The issue with 3I/Atlas was not just the magnitude of the acceleration. It was the direction. The non-gravitational acceleration had a substantial sideways component. It was not oriented the way outgassing pressure should orient it. Outgassing pushes a comet primarily in the anti-sunward direction, because the Sun heats the Sun-facing side and the gas jets off that side. The reaction force points away from the Sun. Clean, predictable, measurable. The acceleration detected in 3I/Atlas post-perihelion had a component that was not pointing away from the Sun. It was pointing sideways. Not dramatically, not unmistakably. The uncertainties in the measurement were real and the skeptics were right to raise them, but the direction was inconsistent with simple thermal rocket effects from solar heating. Kaku, looking at this data, found himself in the most uncomfortable position a scientist can occupy. He had made a specific public prediction, the data had not clearly falsified it, and now he had to decide what to say next. He did not declare victory. He called for more observation, more data, more transparency, more analysis in the peer-reviewed literature where every assumption could be examined, every error bar interrogated, every alternative explanation stress-tested. But he also said plainly, the anomalies are real. They are not going away, and the scientific community owes the public and itself a serious, systematic effort to explain them or acknowledge that they cannot be explained. He accused NASA, gently but unmistakably, of anchoring too quickly on the comet hypothesis and releasing too little of the raw data that would allow independent researchers to check the measurements. This is a serious institutional critique. It is the kind of critique that gets scientists unfriended at conferences. And Kaku made it anyway. On the other side of the argument, we have to be honest about what the skeptics said. Because the skeptics made real points, and intellectual honesty requires sitting with them. Jason Wright, an astronomer at Penn State who specializes in technosignatures, who is, in other words, one of the people most professionally invested in taking the question of alien technology seriously, wrote a careful, detailed analysis of Loeb's anomaly list. He pointed out that measuring the position of a fuzzy, extended object like a comet coma is notoriously imprecise. When you try to calculate a position for something that looks like a cloud with a blurry center, different measurement techniques give you different numbers, and the resulting uncertainty in non-gravitational acceleration is likely larger than the formally reported error bars suggest. The measurement might be real, or it might be an artifact of trying to precisely locate something that is not precise by nature. He also argued that many of the other anomalies, the anti-tail, the color shift, the nickel, while individually curious, each had plausible natural explanations that did not require exotic chemistry, let alone artificial origin. The anti-tail might reflect an unusual dust-size distribution, with large particles that do not respond strongly to radiation pressure. The blue-ward color shift might reflect the rapid exposure of fresh subsurface ice as the outer crust evaporated near perihelion. The nickel abundance, while elevated, was within the range of what could be produced by certain organic compound breakdown mechanisms. Wright was right to make these arguments. Science proceeds by proposing natural explanations and testing them rigorously. And none of the individual anomalies, examined alone, is beyond the reach of natural models. Each one, taken separately, can be explained away. But here is the thing that Loeb kept pointing out and Kaku kept echoing, and that no amount of individual anomaly dismissal can fully address. The anomalies were not separate. They were simultaneous. They were all present in the same object at the same time during the same transit through our solar system. The probability of a single comet simultaneously exhibiting a persistent anti-sunward jet, an anomalous blue-ward color shift near perihelion, an elevated nickel abundance, a non-gravitational acceleration with a sideways component, a CO2/H2O ratio 4.5 standard deviations above solar system norms, a trajectory whose closest approach to Jupiter matches Jupiter's Hill radius to within 0.1%, and an origin in the oldest stellar population of our galaxy. The probability of all of these occurring together in a single natural object is the product of their individual probabilities. And Loeb, who cataloged 22 anomalies by March 2026, calculated that combined probability to be extraordinarily small. This is the crux of the debate, and it is a debate that cannot be settled by dismissing each anomaly one by one. It requires explaining why all the anomalies co-occur in this particular object at this particular time. Let us talk about the Jupiter encounter, because this is where the story becomes genuinely strange. The kind of strange that makes you set down whatever you are doing and just sit with it for a moment. After 3I/Atlas swung around the Sun on October 29th and emerged from solar conjunction, astronomers refined its trajectory with extraordinary precision. ESA's ExoMars Trace Gas Orbiter, using Mars orbit data from October 1st through 7, improved the orbital solution by a factor of 10 compared to earlier estimates. The refined trajectory told a story that immediately caught Loeb's attention. On March 16, 2026, 3I/Atlas would make its closest approach to Jupiter. The forecasted distance, 53.445 million kilometers, with an uncertainty of just 0.06 million kilometers. That is a prediction accurate to within 60,000 kilometers out of 53 million, a precision better than 0.1%. Jupiter's Hill radius, the boundary of Jupiter's gravitational domain, the sphere within which the planet can hold satellites in orbit stable against the Sun's competing gravity, is approximately 53.502 million kilometers. The coincidence, the object's closest approach to Jupiter, shaped in part by the non-gravitational acceleration it had received near perihelion, was essentially identical to Jupiter's Hill radius. The match was to within 57,000 kilometers. The statistical probability of a random interstellar object achieving this level of precision by accident, according to Loeb's analysis, less than 0.00004, less than 1 chance in 25,000. Loeb pointed at this number and did not blink. He pointed at it on Medium. He pointed at it in submitted papers. He pointed at it in public lectures. And he said what the number, if it is to be believed, implies. Jupiter's Hill sphere is not just a boundary on a diagram. It is a dynamic environment. At the Hill radius, specifically at Jupiter's gravitational Lagrange points L1 and L2, small objects can maintain stable orbits with minimal fuel expenditure and minimal orbital correction requirements. These are, in the engineering sense, the most efficient parking orbits available in Jupiter's gravitational neighborhood. If you wanted to deploy a network of observation platforms or data relay stations in the outer solar system, if you wanted, hypothetically, to establish infrastructure near the largest planet in the system that could be maintained indefinitely with minimal energy investment. Jupiter's L1 and L2 Lagrange points at the Hill radius are exactly where you would aim. Loeb wrote, 3I/Atlas may intend to release technological devices as artificial satellites of Jupiter, potentially at Jupiter's Lagrange points L1 and L2 at the Hill radius. He used the word intend, a Harvard professor of science. In print, with his name on it, that word lands differently than any amount of spectral data, because intend is not a word that belongs to physics. It is a word that belongs to minds. To understand why Kaku's warning carries the weight it does, and why the scientific community's response was as complicated and conflicted as it was, we need to step back and think about the history of science in moments of genuine, irreducible ambiguity. Because 3I/Atlas was not the first time that the universe handed astronomers something that did not fit, and the historical precedents are instructive. In 1967, at the Mullard Radio Astronomy Observatory in Cambridge, England, a graduate student named Jocelyn Bell Burnell was combing through reams of chart recorder output from a radio telescope, looking for quasars. She found something else, a signal pulsing with metronomic precision, once every 1.3373 seconds, regular as clockwork, unwavering, reproducible. Natural radio sources are not supposed to pulse like that. Natural radio sources are messy, chaotic, varying on timescales that reflect the turbulent physics of gas clouds and stellar atmospheres. A signal as regular as a heartbeat implied something else. It implied a mechanism, a structured, repeating, physically precise emitter. The first internal designation given to this object, only partially in jest, was LGM-1. Little Green Men 1. Bell Burnell and her supervisor Anthony Hewish were serious scientists. They did not believe they had found aliens, but they sat with the possibility long enough to think carefully about it, to analyze the signal from multiple angles, to rule out artificial terrestrial interference, to consider and then reject the extraterrestrial intelligence hypothesis. And only then did they move on to understanding what they actually had. Pulsars, rotating neutron stars, collapsed stellar remnants spinning dozens or hundreds of times per second, their radio beams sweeping the galaxy like cosmic lighthouses. Nature, it turned out, could produce something that looked, at first encounter, like a message. The lesson of pulsars is double-edged. On one side, the universe is strange enough, physical enough, that phenomena which superficially resemble structured, artificial signals can arise from purely natural processes. The impulse to invoke intelligence when confronted with regularity is a known cognitive bias. It is called apophenia, the tendency to perceive patterns in random noise. We need to guard against it in science as rigorously as we guard against confirmation bias and p-hacking. On the other side, the scientists who found the pulsars were the ones who took the anomaly seriously enough to analyze it carefully, to ask the uncomfortable question, to sit with the uncertainty rather than immediately discarding the strange signal as a calibration error. If they had not, the discovery might have been delayed by years. The careful engagement with the anomalous result, even the result that turned out to be natural, is what produced the knowledge. Oumuamua presented the same double-edged lesson 8 years ago, and it was resolved differently. When Oumuamua arrived in 2017, it was also anomalous, also puzzling, also the subject of competing natural and non-natural explanations. It exhibited non-gravitational acceleration with no detectable outgassing, the equivalent of a car accelerating with no visible engine or exhaust. Its shape, inferred from brightness variations, appeared to be flat and elongated in proportions unlike any known comet or asteroid. Its color was red. Its trajectory was hyperbolic. The mainstream scientific community worked very hard to produce natural explanations. The leading candidates, a hydrogen iceberg, outgassing in a form our instruments could not detect. A fractal aggregate of porous material, light enough to be pushed by radiation pressure. A fragment of nitrogen ice shaved off a planet in another star system. A thin, flat object, a natural pancake, pushed by sunlight in the manner of a solar sail. None of these explanations was entirely satisfying. None of them was independently confirmed. Oumuamua left before we could gather more data. And today, 8 years later, the nature of Oumuamua is still not settled. The scientific literature still contains papers proposing and refuting various explanations. The controversy is unresolved and probably unresolvable, because the object is gone and the data we collected was insufficient to definitively distinguish between hypotheses. Avi Loeb, who went public with his hypothesis that Oumuamua might be a light sail, a technologically constructed thin sheet of material propelled by radiation pressure, was pilloried by much of the scientific community. He was accused of speculation, of sensationalism, of misusing his Harvard platform to promote ideas that lacked sufficient evidential support. He responded by noting that every alternative explanation had at least as many weaknesses as his, and that the scientific community's discomfort with his hypothesis was not itself evidence against it. Then 3I/Atlas arrived, and Loeb was ready. He had spent 8 years thinking carefully about how to distinguish natural from artificial interstellar objects. He had developed a classification framework. He had identified the specific measurements, non-gravitational acceleration, spectral anomalies, trajectory precision, compositional oddities, that would be most diagnostic. He had argued in papers and lectures and books that the scientific community needed formal protocols for evaluating these objects against the full space of hypotheses, not just the natural ones. When 3I/Atlas arrived, he published 11 scientific papers about it in the months that followed. 11. While the mainstream community was still establishing basic orbital parameters and debating whether the coma was real, Loeb was cataloging anomalies, estimating probabilities, and building the most detailed public case ever made that a specific astronomical object might be artificial. This is why Kaku's warning resonated so strongly. Not because Kaku agreed with Loeb on the conclusions. He didn't, not entirely, not at first. But because Kaku understood, from long experience as a science communicator, that the public debate Loeb was forcing into the open was a necessary one. The question of whether interstellar objects could be technological artifacts was no longer a fringe curiosity. With 3 confirmed visitors in 8 years, and a growing list of anomalies in the most recent and most extensively studied of them, it was a question that mainstream science needed to engage with rigorously, publicly, and without the protective shelter of dismissal. Here is a concept that Michio Kaku has explored in various forms throughout his career, one that sits directly beneath the surface of the 3I/Atlas debate: the von Neumann-Bracewell probe. John von Neumann was one of the most productive mathematicians of the 20th century. In the 1940s and 50s, he laid the theoretical groundwork for self-replicating machines, systems that could use locally available materials to build copies of themselves and send those copies onward. In the context of interstellar exploration, this produces a striking calculation. A single civilization launching a single self-replicating probe could, within a few million years, have its descendants explore the entire Milky Way. The mathematics are not science fiction. They are combinatorics. Ronald Bracewell, a radio astronomer working in the 1960s, proposed a simpler variant. Not self-replicating, but autonomous. A probe sent to the solar system of an interesting star with instructions to wait, to observe, and to respond when the local civilization develops the technology to communicate. The Bracewell probe is a patience machine. It might wait 1,000,000 years. It might wait 1,000,000,000. And then one day, the locals point their instruments at the sky and see something odd. Something that doesn't quite fit the known models. And the probe's job is almost done. The appeal of this concept for a civilization trying to understand a universe that is billions of light years across is profound. Radio waves travel at the speed of light. A civilization broadcasting from 10,000 light years away sends messages that take 10,000 years to arrive, and any response they can expect will arrive 10,000 years after that. For any practical purpose, two-way radio communication across galactic distances is impossible on timescales relevant to a civilization. A probe parked in the target solar system changes the calculation entirely. A probe that has been orbiting our sun or drifting through our system on a hyperbolic pass for the last 1,000,000 years, waiting for the moment when the local civilization develops radio telescopes and space launch capability and automated sky surveys, can observe and record in real time. It can gather data about us, our radio emissions, our spacecraft, our scientific activity, and when it departs, carry that data home without any communication delay. Or it can leave behind relay stations, near the gravitational anchors of the system, that continue gathering data long after the main probe has departed. This is not fantasy. This is the logical consequence of taking seriously the possibility that technological civilizations have existed in our galaxy for billions of years, which is what the age of the universe straightforwardly implies. Kaku has said this plainly. If even one civilization arose in the Milky Way before us and survived long enough to develop interstellar capability, the galaxy may be full of their artifacts. Old artifacts, ancient artifacts, artifacts so thoroughly processed by billions of years of cosmic radiation and interstellar dust impact that they look, to our instruments, like very strange comets. The autonomous observer is not looking for us to notice it. It is simply doing its job, which it has been doing since before our solar system formed. Now let us talk about what Kaku's warning really means at the deepest level. Not what it means about 3I/Atlas specifically, but what it means about how science is practiced, how institutions behave, and how human civilization responds when confronted with genuine uncertainty at the frontier of knowledge. Science is a method. It is not a collection of facts. It is not a body of established truth. It is a process, a set of procedures for distinguishing reliable knowledge from wishful thinking, for building models that survive contact with reality, for updating beliefs when new data arrives. The method works. It has worked spectacularly, producing the entire edifice of modern technology from nothing but careful observation and rigorous mathematics. We owe essentially everything we have, every drug, every device, every mechanism by which you are consuming this content, to the scientific method applied consistently over centuries. But the method is practiced by humans, and humans have professional interests. They have careers to protect, reputations to maintain, funding to secure, graduate students to mentor, colleagues to impress. They operate within institutions that have cultures, hierarchies, taboos. And one of the most powerful taboos in mainstream academic science is the taboo against publicly entertaining the possibility of alien technology in a context where the evidence is ambiguous. This taboo is not irrational. It exists because of history. The history of science is littered with claims of anomalous phenomena that turned out to be mundane, and the scientists who made those claims often suffered for it. The Martian canals, the N-rays, cold fusion, dozens of episodes where extraordinary claims were made on the basis of anomalous data, and the claims turned out to be wrong, and the claimants spent years or decades being the cautionary tale that graduate students are told about during seminars on scientific rigor. The taboo protects science from wasted energy and misallocated attention. But it also creates a systematic bias. When evidence is genuinely ambiguous, when a phenomenon could be natural or could be artificial, and the data does not definitively distinguish, the taboo pushes scientists toward the natural explanation by default. Not because the evidence demands it, but because being wrong in the direction of "it's just a comet" carries no professional cost, while being wrong in the direction of "it might be a probe" can be career-ending. Kaku is aware of this dynamic. He has spoken about it explicitly. He is saying, in the case of 3I/Atlas, the cost-benefit analysis of intellectual caution has been miscalibrated. The potential cost of incorrectly dismissing an artificial object, of sending away the most important thing humanity has ever encountered, without giving it the scrutiny it deserves, because we were afraid to look ridiculous, is incalculably higher than the cost of being overly curious about what might turn out to be a very old comet. He is asking the scientific community to have the courage of their own curiosity, to treat the anomaly list not as a series of minor puzzles to be individually explained away, but as a coherent challenge that deserves a coherent response. There is a deeper philosophical dimension to this that Kaku has circled throughout his career without always naming directly. The question of what the detection of extraterrestrial intelligence would actually mean. Not for the tabloids, not for Hollywood. For us, for the species, for the self-understanding of a civilization that has never, in its entire recorded history, had to confront verified evidence that it shares the cosmos with other minds. Every Copernican revolution in history has been disorienting and ultimately liberating. Copernicus told us Earth is not the center of the solar system. Galileo confirmed it with a telescope. Darwin told us we are not the apex of a divine creation but the current episode in an ongoing biological process that has no predetermined endpoint. Hubble told us the Milky Way is one of billions of galaxies, not the whole of creation. Each time, the territory of human specialness shrank. Each time, the universe got bigger and more indifferent and more interesting. The confirmation that we are not alone, that other minds have existed in the galaxy, that they built things and sent them into the void, that those things are now passing through our solar system, would be the final Copernican revolution. Not the end of human specialness, but the end of human uniqueness. We would join what Carl Sagan called the galactic community of civilizations, though we would join it at an almost certainly very junior rank as the new arrivals, the newcomers, the civilization that just figured out how to send probes of its own. This would explain the Fermi Paradox, or at least one version of it. Enrico Fermi's famous question, if the universe is full of intelligent life, where is everybody? Has dozens of proposed answers, from the Great Filter to the Zoo hypothesis to the Rare Earth hypothesis. One answer that the 3I/Atlas episode makes newly relevant. Maybe they are here, not in the dramatic way of popular imagination, not landing on the White House lawn or broadcasting their existence in unmistakable signals, but quietly, in ways that look like background noise to a young civilization still learning how to read the cosmos. In ways that look, to our current instruments, like interstellar comets with unusual chemistry and slightly wrong direction tails and perihelion trajectories that happen to match Jupiter's Hill radius to within 0.1%. The autonomous observer does not announce itself. That would be counterproductive. You do not want to cause panic in a civilization that is not yet stable enough to handle the information. You observe. You record. You pass through or you park yourself in an efficient orbit, and you wait for the locals to mature. And if they are curious enough and careful enough and brave enough, if they build the right instruments and ask the right questions and resist the institutional pressure to explain away what they cannot immediately explain, they might notice you. We noticed 3I/Atlas. We argued about it for months. We filled terabytes of disk space with its spectrum and its photometry and its non-gravitational acceleration profile. We had Nobel laureates and physics professors on cable television debating whether it was a rock. Perhaps that is the point. Perhaps that is the signal, and we are the ones who cannot yet read it. Here is what we should have done, and what we must commit to doing the next time. We should have launched a spacecraft to intercept 3I/Atlas. This is not a fantasy. Multiple serious technical analyses, published in the weeks after discovery, showed that a rapid response mission was physically achievable. The object was large enough and bright enough to be tracked with great precision. Its trajectory through the inner solar system was known accurately enough, early enough, to calculate intercept trajectories using existing high-energy launch systems. The propulsion requirements were steep. A fast interplanetary mission on a weeks-long timeline is not something current spacecraft are designed for, but they were not beyond the capability of systems that exist. Several scenarios were proposed. A flyby at a few thousand kilometers using a small dedicated spacecraft launched on a Falcon Heavy or similar vehicle could have returned high-resolution images of the nucleus surface, in situ spectroscopy of the coma at close range, radar sounding of the internal structure, and thermal mapping that might reveal hotspots inconsistent with a simple icy nucleus. A larger mission with more lead time could have executed a rendezvous, matching velocity with the object for an extended observation period. We did not launch. The reasons are real. Mission approval processes at NASA and ESA require years, not months. Funding redirections of the magnitude required trigger congressional review. International coordination for a mission of this scientific importance would require months of negotiation that the Discovery timeline did not allow. These are not excuses. They are the honest description of how large government bureaucracies operate, and they are also precisely why those bureaucracies cannot respond to the universe on the universe's schedule. Kaku and others have argued that we need a standing rapid response infrastructure. A spacecraft or a component of a spacecraft permanently stationed at the Earth-Sun L2 Lagrange point, or in a high Earth orbit with sufficient delta-V stored in its propulsion system, ready to deploy within weeks of a discovery. The ESA Comet Interceptor mission, approved in 2019 and designed partly with interstellar objects in mind after the shock of Oumuamua, is supposed to provide this capability. It is scheduled for launch in the late 2020s. It represents exactly the right thinking, applied after exactly the right lesson was learned. But it was not ready in 2025 when 3I/Atlas arrived. And 3I/Atlas did not wait. The thing that might have definitively answered the question, going there, flying through the coma at close range, photographing the nucleus with a camera capable of resolving features at meter scale, detecting whether what we were looking at was a tumbling dirty snowball or a structure with geometry that nature does not produce. That capability did not exist when we needed it. This is the tragedy at the center of the 3I/Atlas story. We saw it. We tracked it with magnificent precision. We gathered extraordinary amounts of data from a distance. And the one measurement that would have mattered most, close up, in situ, undeniable, was beyond our reach. The next one will come. Statisticians who have modeled the rate of interstellar object detection predict that Atlas and its successors will catch approximately one interstellar object of detectable size every 5 years or so. As survey capabilities continue to improve, the next one might be smaller. The next one might be faster. The next one might pass closer. The next one might give us 6 months of warning instead of the weeks that 3I/Atlas provided. When the next one comes, we need the spacecraft already waiting. The story of 3I/Atlas is not over. It will not be over for years, perhaps decades. The object made its closest approach to Jupiter on March 16, 2026. The Paradox distance, the closest point of the Jupiter encounter, was measured as it occurred, and that number, compared against the Hill radius, will be scrutinized by researchers for years. If the match between Paradox distance and Hill radius held as precisely as the pre-encounter predictions suggested, Loeb's anomaly list gains an entry that is harder to dismiss than any of the others. If the object's trajectory was modified by the Jupiter encounter in some unexpected way, if it released material, if its brightness changed in a way inconsistent with gravitational tidal effects, if anything unusual was detected in Jupiter's environment in the weeks following the encounter, those observations will be published, analyzed, argued over, and eventually either explained or added to the ever-growing catalog of things about 3I/Atlas that we cannot fully account for. The James Webb Space Telescope observations will continue to be analyzed. The SphereX infrared data will be mined for composition signatures. The non-gravitational acceleration measurements will be re-examined with better error analysis and compared against updated outgassing models that account for 3I/Atlas's unusual CO2/H2O ratio. Every paper that Avi Loeb has submitted about this object will go through peer review, and the reviewers' critiques will either hold up or they will not. Science is slow. Science is frustrating. Science does not give you answers on your schedule. It gives you answers when the data and the analysis and the critical examination by the community are complete. And for an object as observationally challenging as 3I/Atlas, a fuzzy, fast-moving, chemically exotic visitor that spent only months in range of our best instruments, the complete analysis will take years. Meanwhile, the object itself is gone. As of early 2026, it was heading outward past Jupiter, accelerating away from the Sun, carrying whatever it carries: organic-rich processed ice, ancient stellar dust, a cosmic ray-processed crust hiding whatever lies beneath, back into the interstellar darkness. By 2030, it will be beyond Neptune. By 2050, it will have crossed the heliopause and returned to the interstellar medium. By 3000 AD, it will be heading toward whatever star system comes next on its trajectory, if any lies in its path. Wherever it came from, whatever stellar system gave birth to it or manufactured it or ejected it or launched it, we'll never know in any practical sense what happened here. The universe is too large for that kind of communication. The distance is too great and the time is too long. But we know. We were here. We saw it. We pointed every instrument we had at it, and we recorded everything we could record, and we argued about it at the top of our lungs. We did what humans do when they encounter something they do not understand. We asked every question we could think of, and we wrote down the answers, and we disagreed about what the answers meant, and we kept asking. That is the most human response possible to the most cosmic of questions. And it is, in its own way, beautiful. That is the most human response possible to the most cosmic of questions. And it is, in its own way, beautiful. There is one more thing we need to talk about before we reach the end of this story, and it is perhaps the most scientifically interesting detail of the entire episode. It is the thing that neither side of the debate, not the comet advocates, not the probe theorists, can fully account for. It is the question of what 3I/Atlas actually looks like underneath. The James Webb Space Telescope, in its observations of 3I/Atlas, confirmed what the Atlas photometry and ground-based spectroscopy had been suggesting. The object surface is not pristine. It has been transformed. The cosmic ray processing study by Romain Magillo and his collaborators at the Royal Belgian Institute for Space Aeronomy was devastating in a particular specific way. What they found that the outer 50 to 65 feet of 3I/Atlas's nucleus has been so thoroughly irradiated by galactic cosmic rays over billions of years that it no longer reflects the composition of the star system that created it, means something fundamental about the limits of what we can learn. We cannot see inside, not even with the James Webb Space Telescope. The processed crust acts as a shield, and everything outgassing from the surface is drawn from that processed material, not from the pristine interior. When we look at 3I/Atlas's spectrum, we are looking at a material record of its journey, not its origin. We are reading the scars of billions of years of radiation, not the birth certificate of the system that created it. This is philosophically significant in a way that transcends the immediate scientific question, because it means that even if 3I/Atlas is entirely natural, a comet, nothing more, born around a dead star in the galactic thick disk, wandering for 10 billion years until chance brought it here, we cannot determine that from spectral observation of its surface. And equally, if it is artificial, if somewhere beneath that cosmic ray crust there is structure, geometry, material composition indicative of manufacture, we cannot determine that either. The irradiated mantle is opaque to our remote sensing capabilities. The only way to know what is inside 3I/Atlas is to go there and look, to crack the cosmic egg, to drill through the processed surface and sample what lies beneath. This is not something a flyby mission could do. It would require a rendezvous matching velocity with the object, which at 58 kilometers per second relative to the Sun at solar system escape velocity is a propulsion challenge far beyond what we sent to Rosetta and Comet 67P. It would require technologies that we are developing but do not yet have operational. It is, in the language of mission planning, a future generation problem. But here is the thing, 3I/Atlas is not the last one. The statistical argument is clear. There will be another, and each time we detect one, we will have a choice. We can observe from afar, gather what data our instruments allow, argue about the anomalies, and watch it leave. Or we can go there. Kaku has argued for going there. He has argued for it not just as a matter of scientific curiosity, though it is certainly that, but as a matter of civilizational priority. He has pointed out that the technologies required to rendezvous with an interstellar object, high-thrust propulsion systems, advanced solar electric propulsion, miniaturized instrument suites that can be launched on months-long timelines, are technologies with enormous value beyond this single application. They are the technologies of a spacefaring civilization. They are the technologies that will eventually allow us to explore beyond our own solar system. Building them for this purpose and funding them with this motivation is not a distraction from other priorities. It is itself one of the most important things we could do. He said something similar about SETI, the search for extraterrestrial intelligence, for decades. Not that we were definitely going to find anything, but that the search itself, the act of systematically listening, of building the instruments, of asking the question in a rigorous and sustained way, was worth doing independent of whether any individual search succeeded. The search is the discipline. The discipline changes what we know how to do, and what we know how to do opens doors we could not otherwise open. The same logic applies to interstellar object intercept capability. Even if the next 10 interstellar objects we intercept turn out to be perfectly ordinary ancient comets with no trace of anything unusual, the act of going to them teaches us propulsion, teaches us in situ instrumentation in deep space, teaches us autonomous mission management in environments where round-trip communication delays with Earth make real-time human control impossible. All of these capabilities are prerequisites for human interstellar exploration. We are building the skills of the future while answering the questions of the present. And if one of the objects we intercept turns out to be something else, if the mission returns images of a surface geometry that has no natural explanation, or a density profile consistent with hollow chambers, or material composition that could not have formed in any known astrophysical environment, then we will be the generation that answered the oldest question in the history of human curiosity. Are we alone in the universe? That answer, whatever it is, changes everything. The Fermi Paradox has hung over the SETI community like a philosophical storm cloud since Enrico Fermi posed the question over lunch at Los Alamos in 1950. If intelligent life is common in the galaxy, and if even a small fraction of civilizations develop interstellar travel capability, And if the galaxy is old enough for such civilizations to have colonized it many times over, where is everybody? The question has generated dozens of proposed answers in the 75 years since Fermi asked it. The Great Filter, perhaps the emergence of complex life or technological civilization, is so improbable that we are effectively alone, and the filter is behind us, not ahead. The zoo hypothesis. Advanced civilizations are deliberately avoiding contact with us, maintaining us as a wildlife preserve. The dark forest. Civilizations stay quiet because any civilization that reveals itself risks destruction by others. The transcension hypothesis. Advanced civilizations turn inward, exploring the inner space of virtual realities and quantum computing, rather than expanding outward into physical space. The signal is too weak. We have been listening for radio signals for only 60 years, covering only a tiny fraction of the galaxy's stars, and we should expect to find nothing yet. Michio Kaku has engaged with all of these answers over the course of his career. He does not commit firmly to any of them. He is, at his best, a person who takes uncertainty seriously and helps others do the same. But in the context of 3I/Atlas, he articulated something that draws on these frameworks in a specific and interesting way. He pointed out that a civilization millions or billions of years ahead of us in technological development would not necessarily be doing what we are doing. They would not necessarily be broadcasting omnidirectional radio signals from their home planet, waiting for the neighbors to respond. That is what a young technological civilization does. A civilization that has just discovered radio waves and is excited and naive enough to shout into the void. A civilization with billions of years of experience would likely have moved far beyond this. They would know that the galaxy is large and slow, and that real communication requires presence rather than signals. They would send probes, physical objects, autonomous systems capable of observation and data collection. Systems designed to survive the billions of years of interstellar travel required to reach distant star systems, arriving as ancient and transformed and superficially natural-looking objects that the local civilization might mistake for debris from their own system's formation. If this is what advanced civilizations do, and it is at least as reasonable a hypothesis as the alternatives, then the silence of SETI is not a paradox at all. We have been listening for the wrong thing. We have been listening for radio signals when we should have been looking for rocks with anomalous tails and sideways non-gravitational accelerations and Jupiter Hill radius encounters accurate to 0.1%. We may not be in contact with extraterrestrial intelligence because we have not yet learned the right way to look. The communications infrastructure of the galaxy may not be radio. It may be physical. It may be the slow, patient movement of manufactured objects through the dark between stars, arriving at solar systems that contain interesting planets, recording what they find, departing on hyperbolic trajectories that carry the data home. If so, 3I/Atlas is not the exception. It is the system, and we have been living inside it for as long as our star has been orbiting the galactic center. What should you do with all of this? What does a thoughtful person, watching this story unfold in real time, take away from Michio Kaku's warning and 3I/Atlas's strange passage through our cosmic neighborhood? First, stay curious. The universe does not owe you clean answers. It offers data. It offers phenomena. It offers anomalies, data points that do not fit the models, behaviors that defy easy explanation, objects that arrive from places we cannot trace and depart on trajectories we cannot follow. What you do with the anomalies is a choice you make. You can resolve them into comfort, find the nearest natural explanation, apply it, move on, or you can sit with them as genuine open questions. The best scientists, the best thinkers, the best minds humanity has produced are the ones who can sit with the discomfort of not knowing. They do not rush to resolution. They let the question breathe. They understand that an anomaly that is not yet explained is not an error in the data. It is an invitation from the universe. Second, take the institutional critique seriously. Not every scientific question is equally open to being asked in every scientific context. The question of extraterrestrial intelligence, and specifically the question of whether a particular observed object might be an artificial artifact, carries professional risk that a question about dark matter or inflationary cosmology simply does not. This is not a conspiracy. It is not a cover-up orchestrated by shadowy forces. It is sociology. It is the predictable behavior of intelligent humans operating inside an incentive structure that was not designed to handle questions at this frontier. Careers are built on methodological rigor and predictive success. A scientist who publicly entertains the alien technology hypothesis and turns out to be wrong pays a reputational cost that does not recover easily. A scientist who dismisses the hypothesis and turns out to be wrong pays essentially no cost because the dismissal was conventional and convention is not punished. Kaku is asking us to notice this asymmetry, not to abandon rigor, never that, but to extend that rigor in both directions and not let comfort disguise itself as caution. Third, support the infrastructure we will need for the next encounter. The Comet Interceptor mission. Expanded sky survey programs that will catch the next interstellar visitor earlier with more warning when it is farther out, and our trajectory calculations for an intercept mission have more lead time. Standing rapid response mission capability. A spacecraft permanently positioned near Earth, ready to deploy on a weeks-long timeline, fueled and instrumented and waiting. International frameworks for coordinating scientific response to potentially extraordinary objects, so that the first country to detect a visitor is not the only country with data about it. Investment in technosignature research as a legitimate, peer-reviewed, fundable subfield of astronomy. Not a fringe pursuit for those who have read too many science fiction novels, but a rigorous scientific discipline with real methods and real standards. All of these investments pay off regardless of what the next interstellar visitor turns out to be. Even if it is the most boring natural comet imaginable, the capability we build to study it will serve us in every future encounter. Fourth, remember where we are in time. The universe is 13.8 billion years old. The Milky Way is nearly that old. Our sun formed 4.6 billion years ago. Complex multicellular life has existed on Earth for perhaps 600 million years. Anatomically, modern humans have existed for perhaps 300,000 years. Writing and recorded history go back perhaps 5,000 years. The scientific revolution is 400 years old. Rocketry is 70 years old. Automated sky surveys sensitive enough to detect interstellar objects are 8 years old. In the full sweep of cosmic history, we are not merely young. We are barely born. We have barely opened our eyes. Every telescope we have built, every observation we have made, every theory we have developed represents humanity at the very beginning of its scientific life, not anywhere near its maturity. The fact that we detected 3I/Atlas at all, that an automated system built to protect us from local asteroid impacts happened to catch a magnitude 20 interstellar visitor on its very first transit through our observable sky, is a triumph of the most fragile, improbable, extraordinary kind. The fact that we had the James Webb Space Telescope and Hubble and TESS and SphereX and the Psyche mission and the ExoMars Trace Gas Orbiter and hundreds of ground-based observatories to characterize it is a triumph decades in the making, the result of thousands of scientists and engineers and politicians and taxpayers who collectively decided that understanding the cosmos was worth paying for. We are infants who have briefly opened our eyes. And in that brief moment, we saw something wonderful and strange and not entirely explained. We noticed. We looked carefully. We asked the hard questions, even the embarrassing ones, even the ones that made some scientists uncomfortable at conferences. We are still looking, still analyzing, still arguing. That is what science is. That is what it was always for. Not to confirm what we already believe, to find out what we do not yet know. We noticed. We looked carefully. We asked the hard questions, even the embarrassing ones, even the ones that made some scientists uncomfortable at conferences. We are still looking, still analyzing, still arguing. That is what science is. That is what it was always for. Not to confirm what we already believe, to find out what we do not yet know. And here is what we do not yet know. After all of the observations, all of the papers, all of the televised debates and Twitter threads and academic conference presentations, after the Hubble images and the JWST spectra and the ExoMars trajectory refinements and the SphereX infrared scans and the Gemini South photographs, here is the honest, complete, uncomfortable accounting of our epistemic position on 3I/Atlas. We do not know where it came from. We know the stellar population it belongs to, the galactic thick disk, an old population, possibly 7 to 14 billion years old. We cannot trace it to a specific parent star because the galaxy's gravitational dynamics have erased that record over billions of years of travel. We do not know what it is made of inside. The James Webb Space Telescope showed us the processed outer layer, the cosmic ray-irradiated crust of CO2-rich, organic-laden material that developed over billions of years of exposure to galactic radiation. We cannot see below that crust. We do not know if the interior is pristine ancient cometary ice or something else entirely. We do not know why its non-gravitational acceleration had a sideways component. The outgassing models predict an anti-sunward orientation, and the data shows a deviation from that prediction. The uncertainty in the measurement is real, and the skeptics are right to flag it. But the measurement was made with independent instruments, and the anomaly was confirmed by multiple analyses. We do not know why it became bluer than the Sun near perihelion. Every model for cometary color evolution predicts reddening near perihelion, not bluing. The blue shift was real, measured in multiple spectral datasets, and its physical cause remains disputed. We do not know why the forecasted perihove distance during the Jupiter encounter was so precisely matched to Jupiter's Hill radius. The match might be a coincidence at the level of 1 in 25,000. Or it might not be a coincidence. We do not know whether anything happened during the Jupiter encounter, whether the object's trajectory or brightness or chemical emission changed in any way inconsistent with a passive gravitational interaction. The data from that encounter, as of early 2026, is still being analyzed. We do not know what, if anything, was left behind in Jupiter's orbital environment during the encounter. If objects were released into Jupiter's L1 or L2 Lagrange points during the perihove pass, detecting them would require a sustained monitoring program using instruments capable of finding very faint, very small objects in a region of space that we do not routinely observe at high sensitivity. We know it is gone. We know it is heading back into the interstellar dark, accelerating away from our sun, carrying its secrets or its mission log or its cargo, into distances we cannot follow with any spacecraft we currently have the ability to build and launch. These are the things we do not know. And in science, the list of things we do not know is often more important than the list of things we do know. The known facts establish a baseline. The unknown questions define the frontier, and the frontier is where science lives. Michio Kaku has spent his career at the frontier. Not the frontier where the questions are almost answered, where the next experiment will confirm what everyone already suspects. The frontier where the questions are barely formed, where the answers might break the framework we use to ask the questions, where being right means accepting that everything you thought you knew was missing a crucial piece. 3I/Atlas lived at that frontier. It arrived without warning, behaved without precedent, and departed without explanation. It left behind a list of anomalies, a dataset that will take years to fully analyze, and a scientific community that is, for the first time in its institutional history, seriously and formally engaged with the question of whether an observed astronomical object might be artificial. Loeb's Galileo project, which existed before 3I/Atlas and was originally focused on UAP, unidentified aerial phenomena, pivoted hard toward interstellar objects in the months after discovery. His team published papers, developed classification frameworks, advocated for rapid response mission capability. Kaku appeared on every major television platform, issued his warning, made his prediction, watched the data come in, and refused to either overclaim or underclaim. The International Asteroid Warning Network added 3I/Atlas to its monitoring list, the first interstellar object ever to be placed on that list, a formal acknowledgement by the global planetary defense community that this class of objects requires systematic attention. All of this is progress. Slow, frustrating, inadequate to the scale of the question, but progress. The question is being asked. The question is being taken seriously. The infrastructure to answer it better the next time is being built. And the next time will come. That the universe has already decided for us. On December 19, 2025, 3I/Atlas made its closest approach to Earth. At that moment, 170 million miles away, invisible to the naked eye, tracked by hundreds of instruments both orbital and ground-based, it was nearer to our planet than it had ever been or would ever be again. In laboratories in Cambridge, Massachusetts, where Avi Loeb was writing his papers on the object's anomalies, the data was still arriving. In Pasadena at JPL, where navigators were using the ExoMars and Psyche data to refine the trajectory to extraordinary precision, the models were still being updated. In Mauna Kea, Hawaii, where the Gemini North Telescope was capturing new images of the nucleus emerging from perihelion, the spectra were still being reduced. In Santiago, in Hamburg, in Cape Town, in Tucson, in every city on Earth where an observatory pointed its instruments at the night sky, the photons from 3I/Atlas were arriving, photon by photon, frame by frame, carrying whatever information they carried about whatever this thing actually was. And in all of those places, underneath the professionalism and the rigor and the careful language of peer-reviewed publication, something else was present. Something that lived below the equations. Something that a physicist who had spent his entire career thinking about the cosmos would recognize immediately. The particular quality of attention that arises when you are looking at something that might be looking back. Wonder. And its quieter companion. Fear. Not fear of impact. 3I/Atlas posed no threat to Earth. The closest it came was 170 million miles. Not fear of the unknown in the naive sense. The fear of an answer. The fear that the universe might be more populated than we thought. That the apparent silence of the cosmos might be a feature of our own immaturity rather than evidence of cosmic solitude. That something older than our sun, moving through our solar system on a trajectory too precise to be entirely comfortable, might not have arrived by accident. Michio Kaku has been carrying that fear and that wonder for his entire career. He has channeled them into books that have sold millions of copies and lectures that have reached tens of millions of people and television appearances that make the most exotic physics feel personal and relevant. He has turned his discomfort with the possibility of cosmic solitude into a lifelong argument for taking the question seriously, for building the instruments, for launching the missions, for having the conversations that make comfortable people uncomfortable. His warning about 3I/Atlas was not a warning about 3I/Atlas. It was a warning about us, about our tendency to explain away what we cannot explain, about our institutional resistance to sitting with genuine uncertainty at the frontier of knowledge, about our limited window of opportunity to answer the question that may be the most important question in the history of science. Are we alone? 3I/Atlas did not answer that question. It deepened it. It gave us 22 anomalies and a perihelion energy boost and a Jupiter encounter too precise to ignore and a spectral chemistry too exotic to fully explain. And then it continued outward, past the orbit of Jupiter, past Saturn, past Neptune, past the heliopause, back into the interstellar dark from which it came. We are left here, with our telescopes and our theories, with our anomaly lists and our error bars and our arguments in the peer-reviewed literature, with a prediction from one of the world's most prominent physicists that the universe handed us a test, and the uncomfortable feeling that we may not know yet whether we passed. Somewhere out there, past the orbit of any planet, moving now at 137,000 miles per hour through the cold dark between stars, something is traveling. Something ancient. Something that has been traveling since before our planet formed. Something that passed through the neighborhood of our sun, swung around it, received a gravitational slingshot that may or may not have been its only source of acceleration, passed through the Hill sphere of the largest planet in our system, and departed on a trajectory that leads back toward whatever origin story belongs to it. It is not coming back. The orbital mechanics are clear on that. Hyperbolic trajectories do not loop. They escape. 3I/Atlas will never visit our solar system again. But the next one will come. That, too, the mathematics predicts. Another visitor from another star on another hyperbolic arc, arriving in the scan of some future telescope on some future night. And when it does, we will need the spacecraft waiting. We will need the protocols established. We will need the institutional courage to ask every question, including the hard ones, and to resist every temptation to resolve the anomalies into comfort before the data actually demands it. The universe is watching one way or another, and we owe it the dignity of watching back. There is something that rarely gets said in these conversations, amid all the talk of anomalies and probabilities and non-gravitational accelerations and Jupiter Hill radii. Something that Kaku has gestured at in his most reflective moments, and that Loeb has written about in his more personal essays, and that any scientist who has spent a serious amount of time looking at the night sky has felt at some point in their career. The universe did not have to be comprehensible. It is an observed fact, bordering on a miracle, that the same equations that describe the behavior of matter at the smallest scales also describe the curvature of space at the largest scales. that the mathematics developed by people sitting at desks in Cambridge and Princeton and Göttingen, thinking about abstract problems with no obvious practical application, turned out to be exactly the language the universe uses to describe itself. There was no guarantee of this. There is no deep theoretical reason why the cosmos had to be something human minds could make sense of. And yet it is. Einstein noticed this and called it the most incomprehensible thing about the universe. That it is comprehensible. He meant it as a statement about physics, but it applies equally to the question of life and intelligence. There was no guarantee that the universe had to produce beings capable of asking questions about it. There was no guarantee that those beings, once produced, would develop the specific combination of curiosity and discipline that we call science. There was no guarantee that science, once developed, would be powerful enough to detect interstellar visitors from beyond our solar system and measure their spectral signatures with sufficient precision to identify anomalies that deviate from expectation by 4.5 standard deviations. And yet here we are, standing in the particular spot in space and time where the universe has developed the capacity to look at itself, where matter has organized itself into minds that can ask whether the faint smudge of light on a July detector is a comet or something more. That is what 3I/Atlas is at its deepest level of meaning. It is a test not of the physics of cometary outgassing or the mechanics of non-gravitational acceleration. It is a test of whether we have the intellectual maturity to sit with a question this large without flinching away from it. Whether we can bring the full weight of our scientific capability to bear on something that might turn out to be the most important thing we have ever encountered, and still maintain the rigor to say, we do not know yet and we will keep looking. Michio Kaku issued his warning. The warning was heard. The data came in. The anomalies accumulated. The object departed. And we are still here, still looking, still asking. That is not a failure. That is science doing exactly what science does. It is the process by which a species that evolved to track prey on the savanna has managed to extend its senses across light years, to measure the spectral signature of objects billions of years old, to notice when the expected and the observed diverge by a number that demands an explanation. We noticed, we measured, we argued, we will keep going. Because somewhere in the dark, whether it is 3I/Atlas receding toward the outer galaxy, or the next object that has not yet been discovered, or something parked quietly in Jupiter's shadow that we have not yet looked for hard enough, the answer to the oldest question is waiting. Patient as the cosmos, old as the stars. That is what science has always been for. Not to confirm what we already believe. Not to reassure us that the universe is orderly and comprehensible and full of nothing more surprising than we have already imagined. Science is for finding what we did not know to look for catching the thing we were not expecting, for sitting with the data that does not fit and asking with full honesty, with full rigor, with full courage. What does this mean? 3I/Atlas was that data. A faint smudge on a July detector, a magnitude 20 visitor from before our solar system existed, a list of 22 anomalies that resists clean resolution, a Jupiter encounter accurate to 0.1%, a non-gravitational acceleration with a sideways component, a blue color shift near perihelion that no standard model predicts, an ancient object from the thick disk of a galaxy that was already old when our sun formed. Not one of these facts alone is proof of anything. Together, they constitute a question that the universe is asking us, and has been asking since July 1st, 2025, and will continue to ask until we build the spacecraft to go and look. Michio Kaku's warning is, ultimately, a simple one. It can be stated in a single sentence. The universe is handing us tests. We need to be ready to take them. We are the generation that built the instruments to find it. Let us also be the generation that builds the instruments to understand it. And let us have the courage, the scientific courage, the intellectual courage, the civilizational courage, to follow the data wherever it leads, even when it leads somewhere that makes us deeply, productively, magnificently uncomfortable. The universe is watching one way or another, and we owe it the dignity of watching back.